If this is your first time here, this isn't a standalone video. It's one chapter in a complete story, the entire history of evolution, from the first replicating molecules to you. Every organism we mention is your direct ancestor, not a cousin species, not something similar, your actual lineage, an unbroken chain connecting you to the origin of life. That's what makes this different from every other evolution content out there. Most of it is scattered fragments, dinosaurs here, early humans there, the Cambrian explosion somewhere else, all disconnected. But they're not disconnected. They're all chapters in the same story, your story, and you can't understand any link without seeing what came before it. Lungs don't make sense without swim bladders. Mammals don't make sense without reptiles. Each chapter builds on the last, and nothing appears out of nowhere. 4 billion years of your deep history told as one continuous thread. If that sounds interesting, Chapter 1 is in the top right corner. I'd recommend starting there. If you've been watching from the beginning, you already know what this is. Let's keep going. Our lineage now exists as small vertebrates with cartilaginous skeletons, segmented muscles, paired fins, and sophisticated sensory systems. These early vertebrates swim actively through Ordovician seas around 480 million years ago, hunting small prey and evading predators. But they share a critical limitation with all vertebrates for the first 50 million years of vertebrate history. They lack jaws. Every early vertebrate feeds either by filter feeding, straining small particles from water, or by sucking up tiny prey whole. This constraint limits what they can eat, how large they can grow, and their role in ecosystems. The evolution of jaws, one of the most consequential innovations in our lineage's history, transforms vertebrates from peripheral players into dominant predators. Jawless vertebrates, called agnathoms, diversified considerably during the Ordovician and Silurian periods. Some remained small and eel-like, others evolved heavy armor, bony plates covering the head and front body, probably as defense against the giant predatory arthropods and cephalopods that dominated these ancient seas. Some developed elaborate head shields with sensory grooves, suggesting they hunted by detecting electrical fields produced by prey muscles, much like modern sharks. But all fed through a simple opening at the front of the head, lacking any mechanism to bite, tear, or process large food items. The constraint wasn't lack of food. Ordovician and Silurian seas teemed with invertebrates, algae, and other vertebrates, but lack of access to much of it. A heavily armored trilobite was inaccessible to a jawless fish that couldn't crack the shell. A fast-swimming cephalopod could escape a predator that needed to approach close enough to suck it in. Large food items were impossible to consume. The vertebrate that could overcome this constraint would access vastly more food resources than competitors. The solution came from an unexpected source: gill supports. All fish have pharyngeal arches, paired cartilaginous or bony bars that support the gills in the throat region. Water enters through the mouth, passes over the gills where oxygen is extracted, and exits through gill slits supported by these arches. Early vertebrates had 6 or 7 pairs of pharyngeal arches, all serving this respiratory function. The first pair sat just behind the mouth opening, the second pair behind that, and so on. Around 430 million years ago, in the Silurian period, some vertebrate lineages began modifying the first pair of pharyngeal arches. Instead of supporting gills, these arches expanded forward and developed hinges, creating a mechanism that could open and close around the mouth. The upper arch attached to the skull and formed an upper jaw. The lower arch became a lower jaw, hinged to the skull at the back and mobile at the front. The second pair of pharyngeal arches, just behind the first, modified to support and stabilize the jaw joint. This transformation, serial homology, where structures that originally repeated along the body became modified for different functions, is a recurring pattern in evolution. The pharyngeal arches didn't appear suddenly as jaws. They were already present, performing a different function, with existing developmental programs controlling their growth and shape. Evolution modified those existing programs, slightly redirecting development, creating new structures from old parts. The earliest jawed vertebrates, called placoderms, appeared around 420 million years ago in the late Silurian and radiated dramatically through the Denovian period. Placoderms varied enormously in size and form. Some remained small, a few centimeters long. Others grew to massive sizes. Dunkleosteus, perhaps the most famous placoderm, reached 6 to 9 meters in length, with blade-like bony jaw plates capable of shearing through prey with tremendous force. Placoderms dominated marine and freshwater environments for over 50 million years. But placoderms are not our ancestors. They represent an early experiment in jawed vertebrate design that eventually went extinct around 360 million years ago, outcompeted by other jawed fishes. Our lineage during the Denovian belonged to a different group of jawed fishes that split from placoderms early in jaw evolution, the gnathostomes, which include all modern jawed vertebrates, sharks, bony fish, and tetrapods including humans. The advantage jaws provided was access to new food sources through 3 mechanisms: biting, cutting, and holding. A predator with jaws could bite chunks from prey too large to swallow whole. It could cut through shells and armor, protecting soft tissue underneath. It could hold struggling prey while positioning it for swallowing or while tearing it apart. Each capability opened ecological niches previously unavailable to jawless vertebrates. Jaws also enabled suction feeding to become more powerful and controlled. Even modern jawed fish that don't bite often use rapid jaw expansion to create strong suction, pulling prey and water into the mouth. The ability to precisely control mouth volume and shape through jaw movements made suction feeding more effective than the simple pumping mechanisms jawless fish used. Teeth evolved shortly after jaws, initially as modified scales. Fish bodies were covered with small scales made of dentin, the same material that forms teeth, covered with enamel-like substances. Scales near the mouth enlarged and became more pointed, creating structures useful for gripping prey. These prototeeth were not deeply anchored or replaced regularly like modern teeth, but they provided enough grip to prevent prey from escaping once captured. Concurrent with jaw evolution, paired fins became more sophisticated. Early vertebrates had simple lateral folds or fin-like projections from the body, but jawed vertebrates developed distinct pectoral fins behind the head and pelvic fins further back, both supported by internal cartilaginous or bony elements. These paired fins provided stability and maneuverability. A swimming fish generates forward thrust by undulating its body and tail, but this creates instability. The fish tends to roll, pitch, or yaw. Paired fins act as hydrofoils, counteract these unwanted movements, allowing faster, more controlled swimming. Better swimming, combined with predatory jaws, created an evolutionary feedback loop. Effective predators needed to catch prey, requiring speed and maneuverability, driving improvements in fins, muscle organization, and body streamlining. Effective prey needed to escape, requiring the same improvements. The result was an arms race where both predators and prey in our lineage's branch became progressively faster, more agile, and more efficient swimmers. Our specific ancestors during the Devonian belonged to Osteichthyans, or bony fish. This group split from cartilaginous fish early in gnathostome evolution. The defining features is bone, not just cartilage, but true mineralized bone made of calcium phosphate deposited in an organic matrix. Bone is harder and more rigid than cartilage, providing better support and protection. It's also metabolically active tissue that can be remodeled and repaired throughout life, unlike cartilage, which grows slowly and doesn't heal well. Bony fish also developed swim bladders, or gas-filled sacs derived from outpocketings of the gut. By adjusting the gas volume in the swim bladder, a fish can control its buoyancy, maintaining neutral buoyancy at a given depth without constantly swimming to avoid sinking. This energy saving is substantial. A fish with a swim bladder uses far less energy maintaining position than a shark, which must swim constantly or sink. This innovation may seem minor, but it allowed bony fish to occupy different ecological niches, hovering in place to ambush prey or hiding in vegetation without expending constant energy. The swim bladder is evolutionarily crucial for another reason. It's homologous to lungs. The same developmental outpocking that becomes a gas-filled buoyancy organ in most bony fish became a gas exchange organ in others. In our lineage, this outpocketing becomes lungs, enabling air breathing and eventually allowing vertebrates to move onto land. But that's several chapters ahead. Devonian bony fish diversified into 2 major groups: ray-finned fish, and lobe-finned fish. Ray-finned fish have fins supporting by thin bony rays radiating from the body, with muscles for moving the fins located primarily in the body wall. They're efficient swimmers with highly maneuverable fins, and they became the most successful vertebrate group in terms of species diversity. Today, ray-finned fish account for roughly half of all vertebrate species. But our lineage is not with ray-finned fish. We descend from lobe-finned fish, Sarcopterygians, a group that took a different structural approach. Lobe-finned fish have fleshy, muscular fins supported by a core of bones rather than thin rays. The bones within the fins are homologous to bones in your arm, the humerus, radius, and ulna, and smaller bones in the wrist and hand. The muscles that move the fin are within the fin itself, attached to these bones, allowing more powerful and varied movements than ray-finned fish. In the water, these muscular fins provided advantages in certain environments, particularly shallow waters with complex bottom structures, where pushing against substrate or maneuvering through vegetation benefited from fins that could exert force in multiple directions. But the real significance of lobe-finned anatomy becomes apparent only later, when descendants of these fish move onto land. The bones and muscles already present in lobe-finned fish become, with modification, the bones and muscles of tetrapod limbs. By the late Devonian, around 380 million years ago, our ancestors were lobe-finned fish with jaws and teeth, sophisticated paired fins containing bone and muscle, a bony internal skeleton including a backbone of distinct vertebrae, a swim bladder that could be used for buoyancy and potentially for supplementing gill respiration with air breathing, and a well-developed brain with large eyes and other sensory organs. They ranged from small, perhaps 10 centimeters, to medium-sized, perhaps 50 centimeters or more. These fish lived primarily in freshwater environments, rivers, lakes, and swamps. Freshwater poses challenges saltwater doesn't. Oxygen levels fluctuate more dramatically, temperatures vary more widely, water levels change seasonally, sometimes leaving pools isolated, and habitats can become stagnant. These challenges selected for physiological flexibility, particularly the ability to tolerate low oxygen by breathing air at the surface using the swim bladder as a primitive lung. The late Devonian environment was setting the stage for the next major transition. Extensive shallow water environments, rich in vegetation, developed along continental margins. Invertebrates, including early insects, had already colonized land. Plants had established complex ecosystems in wetland areas. Food resources existed on land in the form of plants and invertebrates, but no vertebrate could access them. The vertebrate lineage that could move from water onto land, even briefly, would access an entirely new realm of resources. That transition requires modifications to fins, breathing, skeleton, and sensory systems, changes that would transform lobe-finned fish into tetrapods, the four-legged vertebrates that eventually give rise to amphibians, reptiles, mammals, and humans. But the foundation was already in place. The bony skeleton provided structural support that cartilage couldn't match. The muscular lobed fins contained the bone structure that could be modified into walking limbs. The swim bladder was pre-adapted to functioning as a lung. The sophisticated sensory systems, particularly vision and smell, could function in air with minor modifications. Our lineage stood at the water's edge, literally and evolutionarily. Everything that came before, the origin of animals, the development of bilateral symmetry, the evolution of chordates, the appearance of jaws, the elaboration of bony skeletons and muscular fins, had created a vertebrate capable of exploiting terrestrial environments. The transition from fish to tetrapod, one of the most studied and best documented transitions in the fossil record, is next.